Okay, this is an elastic collision problem. We have two bodies that are colliding. One has a mass of 4 kilograms, the other 5. And the 4 kilogram cart has an initial velocity of 3 meters per second east. And the 5 kilogram cart has an initial velocity of 2 meters per second west. And the assumption here is there's a perfect spring in between them, so no energy is lost in the form of heat or sound in the collision. To solve this, we're going to use these two equations here. The notation I'm using, this one means body 1, and this is body 1's second velocity, body 2's second velocity, body 1's initial velocity, and that's body 1's initial velocity in both cases here. These equations are based on the assumption that the collision is perfectly elastic, meaning the total kinetic energy before the collision is the same as the total kinetic energy after. Total momentum before the collision is the same as the total momentum after. And the initial velocity of body 2 is 0. You take these three assumptions, write out the equations, apply a bit of algebra as we did in class, and you will arrive at these two equations. Now the tricky part is that those equations were derived from the assumption that one of the bodies is at rest. However, when you read this question, you can see that both of the bodies are moving. So we're going to do a little trick here. We're going to change our reference frame to make one of the bodies at rest. So I'm going to label our assumption here. Our assumption is we are observing from the ground. And if we observe from the ground, cart 1, so V11, is 3 meters per second east. And V12 is 2 meters per second west. For simplicity, I'll write that minus 2 meters per second east. That'll make all the arithmetic simpler, having everything going in the same direction. What I want to do now is I want to change my point of view so that as an observer I am making this stay still. And the way you make a body stay still is you run beside it. So imagine I was trying to read this marker, and this marker was moving this way. Well, I would run along beside the marker, and from my perspective, it would not move. So that's what we do here. So our new reference frame, I always call this the train. So I imagine that the observer is on a train, and the train is moving beside the second body. So I want to make the velocity of the second body, so that's actually V21, that's the second body's initial velocity. I'm going to make that equal to 0. And the way I make minus 2 equal to 0 is by adding 2. To the observer on this train, we add 2 meters per second east to all velocities. So to jump on the train, we also observe the other block, the original cart, the first cart. We add 2 to its velocity, and it becomes 5 meters per second. The important thing here, this only works with one-dimensional problems, as simple as this. Use the same direction for all velocities, and then add the same number to all velocities. So what this really means is this. We have two carts, and they're approaching one another. This one was going at 2, and this one was going at 3. If we imagine one as staying still, the other approaches it at 5, so it still takes the same amount of time to cover the distance in between them. But with this assumption, we have a simplification that allows our equations to work. So now that we're on the train, and we've made the velocity of the second cart equal to 0, we can simply apply these equations. So V12 is M1 minus M2. Now M1 was 4 and M2 was 5. And now when we multiply by V11, we're observing this, calculating from the train, so it's got a value of 5. And likewise, the final velocity of the second cart is 2 times m1, so that's 2 times 4 over 4 plus 5. And that's times v11, and v11 is 5. So if you miss the equations here, hit pause, copy them. Okay, so this is negative 1 over 9 times 5. So that's negative 5 over 9. And remember, all of this is east. And the final velocity of the second cart is 8 over 9 times 5. And that's also east. Okay. These are the velocities that would be observed by an observer that's on the train. However, the question mentioned nothing of a train. The assumption is we're to find the velocities with respect to the ground. That's what we were given initially. So we need to convert back. Now, if you label things as such, this becomes very easy, as long as you track all velocities based on the same direction. To jump on the train, you add 2 to all observed velocities. So to then jump off the train, you will simply subtract 2 from all observed velocities. So I'll just draw another line here, and I'm jumping off the train and back onto the ground. And from my point of view on the ground, I will subtract 2 to all east heading velocities. This is why I write everything as east. If one of the velocities was west, then you would have to add 2. So it's simpler, I think, to keep track of directions with positives and negatives, label everything one way, so you're doing the same arithmetic as you change your reference frame. So now with respect to the ground, v12, the final velocity of the first cart, is minus 2 minus 0.55, so that is minus 2.5 repeating meters per second east, which really means it's going west. So it was coming in this way and then it bounced back the other way. And the final velocity of cart 2 is 4.4 repeating minus 2, so it is 2.2 repeating meters per second east. And if you prefer, you could switch that to a positive and write it west at this point. It'd probably make it a little more clear. To recap, on our question originally, we had a perfectly elastic collision. We had a 4 kilogram mass coming this way. It was a cart with a spring to facilitate a perfectly elastic collision, and a 5 kilogram cart coming that way. We wanted to analyze what would happen after they collided and bounced off one another. The analysis is a little bit complicated if both of them are moving. So what we did was we took our observer, okay, so that's supposed to be an eyeball, that's observing, and we put the observer on a train going with the same velocity as this cart. Because those velocities were the same, this appeared to stay still, while this appeared to move faster. This assumption greatly simplified the math, allowing us to use these equations. And I'll put a link to the full derivation of those equations, perhaps in the comments. We then use those equations to find the final velocities of each of these carts, but keeping in mind that those velocities we were observing were relative to our moving observer. We then had to convert them back to determine what those observed velocities would be if observed by an observer that was on the ground.